Hi, my name's Nate, and today I'm going to show you how to use CompactRIO, LabVIEW, and LabVIEW NI SoftMotion to control AKD brushless servomotor drives. So in this setup, I have the CompactRIO acting as an EtherCAT master, which is a deterministic communications bus over a standard Cat5 Ethernet cable. And I have the two AKD drives acting as EtherCAT slaves. And these drives are connected to brushless servomotors behind these disks here. You can see I have the master cable to the first slave, and then the first slave cabled out to the second slave in a configuration called a daisy chain. So now that you know the hardware setup, I'm going to go into LabVIEW and show you how to set up and configure this through the LabVIEW project. So you can see I already have my CompactRIO set up and connected. I'm going to go ahead and add an EtherCAT master device, and that's just the CompactRIO controller here. And you can see that my two EtherCAT devices are automatically detected. I'm going to go ahead and add a SoftMotion axis for each of those EtherCAT devices. And you can see that it's defaulting to the hardware I already have in the CompactRIO chassis. These are motion modules. I'm going to go ahead and change the binding on those to these EtherCAT devices. And you can see that I have a wealth of choices here. I can simulate axes if I don't have hardware connected to the system to do prototyping, or if I want to write some code when I don't have the system available. I have an on-bound axis to do FPGA motion programming, or I have the modules in my chassis, as well as the EtherCAT devices. And today I'm going to just stick to the EtherCAT devices. Okay, as you can see my axes show up in the LabVIEW project. I'm going to go ahead and configure these axes. I need to disable the forward and reverse limit switches because I don't have those in my system. I'm also going to set up the encoder to make the programming a little bit easier to read. I'm going to change the units to revolutions and input my encoder counts per revolution for these motors, which is 10 to the 20th counts per revolution. And I'm going to do the same thing for axis 2. Okay. Now that I've configured the axis, I will go in and test it using the interactive test panel. A good thing to note is that these are brushless servomotors, and so normally you'd have to tune them to your specific load on the specific system. Since I'm using disks right now that don't have much inertia, the default tuning is fine. If you did need to tune your system, you have this interactive gain tuning panel that you can use to test responses, use this slider tuning to set default behavior for your tuning, or you can tune it manually using the control loop gains here. But I'm going to go ahead and use the default gains because I know that they work with these disks. So let's make sure that the axes are configured correctly. I'm going to go into the interactive test panel. This is where you can set up and do a sample move to make sure everything's connected correctly, make sure everything works appropriately. So I'm going to go ahead and make sure that my values here are set up to work with revolutions per second instead of units, which was default. I'm going to enable my drive and go ahead and spin at 10 revolutions, and you can see that the disk moves appropriately. I'm going to test axis 2 as well. Power on that axis. Change all my settings again appropriately. And you can see that that axis also works correctly. So now that we have the hardware set up and configured, let's go into LabVIEW and program a simple motion application. I'm going to go ahead and add an example VI to my CompactRIO. And this example was written in LabVIEW's SoftMotion module, which is the module you use to program any LabVIEW real-time device for a motion application. Okay, so if you look at the block diagram, you can see that I have it programmed using function blocks. It's one of the 3 APIs. You can also use express VIs, or you can use a property invoke node API. Today I'm going to stick to the function blocks though. This is a pretty simple example. What it does is it takes both axes in a resource and then powers them on. enables them. Does a straight line velocity move using both those axes. And I have the ability to stop the move and then stop the VI, which disables the drives. And then in the separate loop down here at the bottom, I'm reading the data back from both axes and graphing it on the front panel. So I think I should be almost ready to run. You can see that I added the VI that has a coordinate space here set up for 2 axes. I don't have a coordinate space in my project yet, so I'm going to have to go in and add a coordinate space, which is very simple. You just add a new SoftMotion coordinate space and add the 2 axes that I have in my project to that coordinate space, and now it shows up in my project. And I can then use that as a resource in my VI. So let's go ahead and run this VI, deploy it to the CompactRIO, and you can see that my drives automatically enabled, and because I had the start move button depressed, they started running, and they're running at the velocity I have set up here on the slider. And the VI is set up with some Boolean logic such that if I change the velocity slider here, the move will automatically update. So I can change to very slow motion or increase the velocity. And note that the axes are coordinated, and that happens automatically because I'm using a coordinate space in SoftMotion and because I have the EtherCAT bus set up, and that bus is automatically deterministic. So I don't have to do any timing and sync to set that up. Okay. And that's how you use LabVIEW SoftMotion, CompactRIO, and AKD brushless servo drives to program a motion application.